muchachos, chicas, señores y señoras. Bueno, vamos a empezar la conferencia con el profesor Peter Bates. Es para mí un honor tener al profesor Peter Bates aquí en la Universidad Distrital. El profesor Peter Bates es una autoridad mundial en análisis matemático, en física matemática, en matemática aplicada, tiene investigaciones en muchas áreas, lo cual es bastante raro en un matemático porque es muy difícil tener investigación en distintas áreas como sistemas dinámicos, física matemática, biología matemática, ¿sí? Entonces vamos a tener el privilegio de escuchar a un profesor de la talla de Peter.
No, this is not the right one. Yeah. I'm playing.
Está jugando con el tablero, le gusta el tablero electrónico.
Yeah.
Por favor, interrumpa cuando me entiendan algo. Cuando me entiendan algo, interrumpa. Yo le pedí, no importa si no importa. Yo le pedí al profesor Bates que la charla le sea lo más elemental posible, ¿sí? Pero entonces el profesor Bates se puede subir con cierta facilidad de nivel sin darse cuenta. Entonces, por favor, interrumpan en cualquier momento. Él sabe que es para estudiantes de pregrado, va a dar una motivación de ecuaciones diferenciales parciales no locales a través de o modelando problemas de materiales. Va a empezar a hacer la charla de hoy. Pero entonces, si en cualquier momento te interrumpan, si no habla el inglés, si no se siente confiado con el inglés o porque va a estar preguntando quién sabe qué cosa, si quiere yo le traduzco y le hago la pregunta, pero por favor, digamos, encarecidamente pregunten. ¿Sí? No se esperen hasta el final porque ya al final ya dejo pasar el momento y seguramente ya no va a haber tiempo. ¿Listo? Bien, está muy emocionado por que ve mucha gente en un puente largo. ¿Sí? Entusiasta de la matemática, entonces está muy contento con eso. ¿Listo? Entonces, sin más preámbulo, profesor Bates.
Okay. No hablo español. So, questions, preguntas? Preguntas is question?
Yes.
So, preguntas in inglés. He will translate in español. Okay, I almost feel bad that you are here because it is a holiday. So I'm sorry. I didn't plan that. Okay, so this is about some non-local partial differential equations. Okay, they're not really partial differential equations, but that's how I'm thinking of them. It's a non-local version of a partial differential equation that I'll speak about. And it's the derivation today from my studies in material science. Ah, hi. It's the ice cream man. So, and this is over a period of time, and this is Fu Xin Chen. He was one of my students. And this is Shin-Fu Chen, and this is Adam Kamai. So these are obviously Chinese. He's from Poland. This is Paul Fife, who is a very famous guy who passed away a couple of years ago. Xiaofeng Ren is a postdoc of mine, and Xufeng Wang was a postdoc of Paul Fife. But it's so some of the theorems are with these people, and some are not. Okay, so let me try. Aha. And I had support from the National Science Foundation, from a research institute in Kyoto, Japan, and Isaac Newton Institute in Cambridge, and that was very nice. And did I spell this correctly?
Mostly.
Mostly, no. The Jose has a thing here. Wait till I get my pen. All right. So this is how I'm describing the evolution of my thinking. So the modeling from first principles, and I spoke with material scientists at a sort of a conference with material scientists and mathematicians, a very small one in the resort in Colorado, and got ideas from material scientists. Bienvenidos, is that welcome? Okay, so I go through the modeling from my view of how physics should work. Who are physicists? Some people here are from physics? Physica? Okay, so you don't listen when I describe, or at least be quiet when I lie. All right, so from first principles, I'll get some equations which will include non-local diffusion, either on a lattice or a continuum. So first a lattice, we'll start with the atomic description, and then once we have these descriptions, we'll talk about how to analyze. So how many people here know what is the calculus of variations? 1, 2, 3, 4. Calculus of variations? No, because there are undergraduates here, so I don't expect so many undergraduates to know the calculus of variations. So I'll talk about the calculus of variations. It's calculus in infinite dimensional space, sort of. Yeah. And then, using these ideas, I'll do some analysis of the non-local equations to get, I'll talk about patterns and waves. Yes, I think I may have time to talk about both of those. Tomorrow, those who are brave will come tomorrow. I don't know what time, but 7 a.m. I think. Did you say so? No. And I'll talk about Turing instabilities. How many people know Alan Turing? More people know Alan Turing. Did you see the movie? Yeah, it's a good movie. Well, in the movie, they didn't tell about two important parts of his life. I mean, the guy was amazing. The movie was about the Enigma code, but he was the father of the electronic computer. They say John von Neumann was, but he had the ideas and he went and talked to John von Neumann. And it's not clear, well, John von Neumann was a brilliant guy himself, but Turing described a programmable machine, a universal machine, which is now called a Turing machine. So that's a fantastic, development. But he also developed the idea of morphogenesis. So the genesis, the creation of morphs, shapes, patterns. And he described the way the coats of animals and fish become patterned, like tigers and zebras and leopards and pumas, and how bones form in embryos. I mean, it forms the basis for that. And tomorrow I'm going to talk about morphogenesis and the Turing patterns or Turing instability. I'm going to talk about it from a little bit, I'll talk about how he looked at it and some of the analysis we can do, and then I'll talk about non-local versions of equations which give Turing instabilities. So, Professor San Juan, Do you pronounce your name San Juan or San Juan?
San Juan.
In Brazil, would they call you San Juan?
San Juan.
Yeah. Okay. So he said that we can stay here for 4 or 5 hours and they will call for pizza and drink. No, kidding. No, it's okay. Okay, so how many people can see 2 colors? How many people can see 2 colors there? You can. All right. I can too, but sometimes when it's red and blue, I can only see black. Okay, so there are 2 colors. The 2 colors represent different species of atoms. Maybe this is gold and this is copper, or what is gold? Oro. Of course I know this. This is El Dorado here. Okay, and say this is oro. This is silver, or 2. Yeah. Okay. So there's lots of different ideas that what they could be, but it could also be a spin system. So atoms have a spin, and they spin up or they spin down. Physicist, okay? Okay. So we can interpret it either way, but it's a lattice with no holes. At every place there is an atom, and it's either spin up or spin down, or it is gold or silver, something like that. So I have this lattice, and come on, yes. Why does this keep changing? I don't know. So between every pair of atoms there is an interaction. Bienvenidos. You thought it was something else maybe. I don't know. You'll have no idea what I'm talking about. So I know it's difficult to get here, and it's hard to get through the gate as well, isn't it? You have to climb over the barbed wire. So between every pair of atoms there is an interaction. Now, how many people have heard of the Ising or Ising system? Ising model. Okay, this is a very famous model, but nobody knows. But physicists tend to play with the Ising model, and probabilists win prizes for finding solutions. Hello, bienvenidos. We're going to have to move to a bigger room. And in that model, it's like this. It looks exactly like this, except it's only nearest neighbor interaction. And almost all of the models that physicists tend to look at are nearest neighbor interaction. They look at a lot of interacting particle systems. Am I speaking too fast? I sometimes do that. So if I'm speaking too fast, you should shout. I don't know what is shout. Okay, despacio. Is that slow down? Despacio. I've seen it on the road signs. So, okay, I'm going to consider very long range interaction, infinite range interaction. Every pair of atoms interacts. Okay, so this is what I mean by non-local. Not just local interaction, but long range interaction. Alright, so there's my system. And now I have a question, I think, that I'm going to ask. Okay, so the first thing is that because of thermal fluctuations, I can't really tell what is at each lattice site. There's an average spin. You know, maybe 3/4 of the time it is spin up, and 1/4 of the time it is spin down. So I say it's what, you know. it's going to be a number, a real number in here. Okay, that's the expected value. Let's say it takes a microsecond to measure the spin there. And then in that microsecond, it's changed a billion times, but you can get the average in your measurement. So instead of it being plus or minus 1, it's a real number between -1 and 1. Okay, now here's a question. So this distribution of spins, of expected values of spins, will evolve with time. It really will. You can see this. You can get a ferromagnet, an iron magnet, and you will leave it on the windowsill for a month, and the magnetism has changed. It is, right? If you warm it, it'll change more quickly. If you cool it, it will change more slowly. So the spins, the magnetic moments of the atoms evolve. And they're a bunch of atoms. Bienvenidos. So why does it change with time? That's the question. Okay. Are there any more physicists, or do I have to pick on this nice young lady every time? No. Okay. Can you tell us why it would change? The configuration of the atoms, why it would change over time? Everybody think and then come up with an answer. Bienvenidos. What do you think? You're sitting in a dangerous position, right in the front line. So I can, I can say, you. In my classroom, I walk around threatening people with my stick. Answer this question. Why would a configuration evolve with time? Any idea? I mean, they could be crazy ideas. It's okay. We are scientists. Scientists have crazy ideas. We're allowed to do that. They're not right most of the time, but at least it's an idea. Anybody?
Si tienen alguna idea de por qué las configuraciones de los átomos cambian con el tiempo.
Yo considero que así no necesariamente no hayan fuerzas o campos que estén afectando a las partículas, ellas siempre tienen, digamos que sus fuerzas propias, entonces las fuerzas de interacción entre ellas.
I'm sure you're right.
Que ciertas cosas estén cambiando, aunque se esté manteniendo un equilibrio general.
I heard equilibrium and cambio, so the changing and the equilibrium. What did he say though? I don't know.
He thinks that maybe it's the interaction of the internal forces of the atoms.
They influence each other. You know what it is? It is they have friends. I only like my kind, so I want everybody to be my kind. Change slowly to become my kind. And we're all my kind, right? We influence, and it happens in society. These could be people instead of atoms. It happens in biology in a very controlled way. But here it is just by laws of physics, by energy methods, a sense of energy. It is the interaction between lattice sites that causes the change, and it is a tendency to dissipate energy. Right? It's uncomfortable if it's all up and down, up and down, up and down. I don't like that, so I relax. So like a relaxation to lower the energy. It just happens. or increase entropy. They talk about increase entropy, but nobody knows what entropy. Everybody thinks they know what energy is, but
¿Es un fenómeno asociado a la entropía?
Sí, sí.
¿Sí?
yeah,
Que tiende a disiparse la energía.
yeah, like
Por ejemplo,
so.
y es que quiero, porque se está planteando en que, bueno, ¿por qué cambia la organización de los átomos a nivel molecular? Bueno, no. Pero digamos que todos esos cambios están bajo un rango para que no cambien las propiedades de los materiales, o sea, porque por ejemplo si ellos cambiaran totalmente la estructura, yo podía pasar de una estructura cristalina a otro tipo de estructura y eso me definiría otro tipo de material, que por ejemplo en nanotecnología se maneja eso, en el cual por ejemplo yo puedo pasar mis partículas que sean cúbicas, pero tengo que hacer un trabajo necesario, es decir, la estructura como tal de los átomos no va a cambiar. Porque si eso se pudiera hacer así fácilmente, digamos que yo podría estar pasando mi mano de un material líquido a un material de acero, como los cómics, algo así. Entonces, digamos, él se refiere a esos cambios en los cuales siguen guardando la estructura principal de la materia.
Sí, lo que está diciendo es que empiezan a relajarse los átomos, a disiparse la energía. Hasta ahora está diciendo eso.
Pero sí, preguntaba que si es derivado de la entropía, que con el paso del tiempo aumenta la entropía general del sistema, pues digamos que la entropía aumenta una forma de aumentar la entropía en cualquier sistema es con la disipación de energía, entonces por eso preguntaba que si tenía que ver con la entropía.
He's asking if it has to do with entropy.
Yeah. Entropy is. I will have entropy in here too.
Yes, because
Yeah.
he's asking if
Increase of entropy.
Yes, increase of entropy.
Increase of disorder. So it becomes sort of uniformly disordered. Maybe. I mean, but it's the interaction energy. So, from what I said, if this is spin up and all the green ones are spin down, then fairly quickly that guy will become green. I've forgotten which was which, but spin down. This will become spin down. And then this guy may go, yes, and here he's got a friend, but he's more surrounded by this. This guy, he has these neighbors and these neighbors. But, on the other hand, there seem to be more green ones. So overall, it depends on the rate at which the interaction decreases with distance as well, right? So the interaction, these arrows, the strength of the interaction will typically decrease with distance, and it may be anisotropic as well. These may be atoms that have landed on a substrate, another material that already has an atomic structure incompatible with this, and so a forced anisotropy of interaction may occur. Probably by being displaced. Okay, so this is if they spin up and spin down. If this is oro and this is
Plata. Silver.
what do you say it?
Plata.
Meta.
Plata is silver.
Oh, in French it's something. Okay. In Latin, AG. Yeah. So, if this is gold and this is silver, then if we wait long enough, this will change to silver. No. It's not influenced by its friends in changing to silver, but it wants to be with its friends who are gold. So maybe these two will interchange. And then we have more homogeneous silver and more homogeneous gold. And it will separate into islands, pieces of gold and pieces of silver. And you have a coarsening of the granular structure. You have volcanoes here, don't you? Granite is an igneous rock. It is formed molten. Who knows what is granite? The rock granite? Granite? I don't know. Not quite this, but this is artificial. Yeah, so you notice there are a lot of crystals in it. And some granite has big crystals, and some has small crystals. The ones with small crystals, the granite cooled very quickly. The one with large crystals, it cooled slowly, because this takes time and it's temperature dependent. So when this changes here, then you get a bigger crystal, and this changes and you get bigger chunks of one substance. If the temperature is high, that can go on. If the temperature is too high, then they go all over the place. You know, you can't do anything with them. But if the temperature is just low enough so that there's some mobility, but not too low, then this will happen. If the rock came up quickly under the sea, and it was molten rock and then came up under the sea and got quenched, cooled very quickly, then you'll have very small grains. And it's because of this kind of interaction. So, two types of dynamics. This is called Kawasaki dynamics, I think, where you switch them. And the other one is, I've forgotten. Anyway, so I'm trying to explain physical ideas and why this might make sense. So, so we're going very slowly to begin with. It's going to evolve with time, and it's going to do this because of dissipation of energy. And then I ask, okay, what did you say? Dissipation of what? Energy? What is energy? Ah, it's the thing in the can. I drink this. And it dissipates. So, but in this sense, that material has an energy, and that energy is going to dissipate. But what is the energy? Well, a long time ago, in a galaxy far, far away, Van der Waals, that's 1893, yeah. He said he was looking at things like this, capillarity, I think, in this particular paper, and he said, we shall obtain a complete solution to the problem like I'm discussing here. How will it evolve? If we can express the free energy, so he had an idea what he was talking about, so he's going to express the free energy at each point as a function of the density. That's like the type of atom at each point, or the average type of atom, you know, because there's fluctuations. So at each point, and the difference of density in the neighboring phases, out to a distance limited by the range of which the molecular forces act. And the molecular forces act infinitely far. The Coulomb potential for electrostatics goes down slowly, but it keeps going down. You never get... So the interaction goes out forever. And he talked about the free energy here. So we had energy, now we have free energy, and this is a physicist talking. And so here is what is the free energy. It's sometimes called Helmholtz free energy. E equals H minus ST. Okay? Now we all know. So H is the potential energy of interaction of all the interactions. There's an energy. You know, if he's spin up and I'm spin down, then there's an energy, a potential energy. It wants to change. Right? It's like being at the top of a mountain on your bicycle, and it's very all the way around, and yeah, you can balance there, but you have a lot of potential energy, which will very soon be converted to kinetic energy when you go down the mountain. So the potential energy of interaction, because of the differences of spins out to whatever distance. S is the entropy, and T is the absolute temperature, When you get to temperature 0, then entropy has no place. You have complete, everything is determined by the interaction. But, yeah.
No me queda claro por qué a mayor entropía, menor energía libre.
He asked why too high energy, less free energy.
Entropy.
Why is it a change? Why is it a difference? Okay, we have to, don't tell people if I'm wrong. Okay. But, so entropy is the rearrangement, the sort of random rearrangement of things. Like chaos, you know, just random rearrangement. The temperature allows that rearrangement. So higher temperature, the entropy is more forceful in jumping things around. And I cannot get that energy that's being taken out from this to do work. So I have potential energy of interaction. I can use that to do some work. But the energy, because of this temperature, of this jumping around, I can't get hold of that. It's like Maxwell's demon. I don't know if you know that thought experiment where you had high temperature in one side of a box and low temperature in another side, and there's a door between these two sides. And there's a little demon, Diablo, and he sees in the cold side, he says, oh, there is a molecule which is moving around fairly quickly. It's coming my way. Open the door, in you go, close the door again. And this becomes hotter, and this becomes colder. Right. Well, there is no demon. You know, heat flows from the hotter to the colder because entropy allows it to. Okay, so this is energy which is unavailable. You get all the interaction energy and you remove that which you can't access. The interaction energy is like this. So lambda is my lattice. The sites in the lattice are R and S. J of R minus S is the interaction energy between site R and site S. So it may be way over there. I look at the vector R minus S and I prescribe, I mean, there is an energy of interaction. I'm not going to answer the question, what is that? I don't know. So if you think of this as a positive interaction energy, and most things are positive, have positive interaction energy, but there are some with negative, then if this is the spin at site R and the spin at site S, if these are the same, then I get something positive here, and I have a minus sign, so that's lower. And I don't care if it's positive, positive, or negative, negative. It's lower when they have the same sign. The energy is lower. So this is the sum over all pairs of points in the lattice of this product. And we divide by 2 because there's a double count. We can do R to S or S to R. There's a double count, and we have a minus because convention says equilibrium states are low energy states. The tendency is to go to low energy. So we put a minus sign there. So this is the interaction energy. What is this function here? Well, it depends. If it's electrostatic interaction, this may be a Coulomb potential, 1 over distance between R and S. It could be like that. Or it could be Van der Waals forces. Or it could be a Leonard-Jones kind of potential. So there are potentials, atoms can't get too close to each other. There is a repelling that happens if they're very close, pushes, but if they're far apart, they may attract. So, okay, so that's believable. That's the energy of interaction. And as I say, J is the possibly anisotropic interaction energy associated with, J of R, yeah. J of R, so of course it's translational invariant and it's symmetric, right? If I interact with this like this energy and he interacts with me with the same energy. Now, here is what is used for the entropy. If I have a distribution, a function u from the lattice to the interval -1, 1, the entropy is minus Boltzmann's constant. Boltzmann constant, yeah. The sum over the lattice, 1 minus u of r log 1 minus u of r plus 1 plus u of r log 1 plus u of r. Now, I have seen that before a long time ago, and I go, why? Who thought that up? Well, you'll notice something about it. When u is equal to 1, then that's log of 0, which is infinite, but this is 0. 0 times infinity is always 0. No. But when this 0 came from a log, it is 0. And this would be what? 2 log 2. It's a number, the negative sign. And when u is minus 1, this is 0, and this is 2 log 2. So that's the, it's sort of symmetric between -1 and 1, and we'd hope that it would be symmetric. You know, the entropy has no preferences. But where did the logs come from? Well, the explanation is, if you first get the proper definition of entropy about the ability to interchange positions in the lattice, then it's all about the number of rearrangements of so many atoms with this sort of average density, average spin, in a box with big N holes in it, big N sites in it. So if I had, and all I know in this box, so each one of those dots, they're not blue or green. It is a number between -1 and 1. You know, they're fractional, or, you know, and they come about because so much of the time it is blue and so much of the time it is green during this quick measurement. And so it's about those exchanges. Maybe in the time of measurement there are 1 billion exchanges, and 1,500,321 times it is blue. But which of those times is it blue? Well, I have to say, I don't know. They could have been in any order. And so the entropy is the ability of those things to rearrange themselves, given that 3/4 of the time, you know, on average, its measurement is 3/4. So the entropy is in there. And how do you calculate the number of rearrangements? We have, you know, 10 billion green balls. We have a box with 10 billion sites, lattice sites, and we have this many blue ones and this many green ones. How many ways of rearranging them? Who knows how to do that problem? At least to write it down. It is combinations, right? You say 10 billion, choose 5, or something like that, right? With factorials. Okay, everybody know about factorials and combinations. Okay, that is nice mathematics we learned in kindergarten or something. All right, that's nothing to do with logs. But how many people know of Stirling's formula? Stirling's formula it is a way to approximate factorials with exponentials, e to the something, right? And there's pi involved and all sorts of crazy things. But it's an asymptotic formula. So combinations, factorials are very hard for analysts. Analysts hate factorials. But if the number is very large, you approximate with pretty good accuracy the factorial by an exponential. Well, the log comes because of that exponential. So, I mean, I could go through the derivation, but boring, but I just want to tell you, it's not just some guy thought that up. It came from in a sensible way. Okay. So I'm going to write down the energy. And in this way, it doesn't look like what I had before. Is that what I had before? Not quite. Yes, it is. It's exactly what I had before. E was H minus ST. Over here you can see the ST. And there's a negative sign, so there's the minus ST. So the rest of it, I didn't tell you what J bar was, but the rest of it is the interaction energy. If I square this, I'll get twice U of R, U of S with a negative. If I divide that by 4, I'll have negative 1/2 U of R, U of S. That's looking familiar. I also get, stop it. I also get U squared of R. But look, here is a double sum. Suppose I have this U squared of R and I do the sum over S first. If I do the sum over S first of U squared of R times this, then I'm essentially just adding this up over the whole lattice. And the interaction energy, we'll have to assume that it decays faster than the Coulomb potential, so that this is a finite sum. And that finite sum is called J bar. So here I have a minus J bar over 2, because I'm taking that out. Oh, but that was a 1/4. But then I have a U of S squared, and in that case I'll sum over R first and get a J bar times U squared over 4, and 2 of them make the J bar U squared over 2. Is that okay? I like it when I can do arithmetic, do algebra. It's anyway, so this is a different way of writing it. So, as I said, the J bar is the summation of J over the lattice. Okay, so now the question is, I want to find out what the minimizer is. How will I minimize this? So let's have some group cooperation here. Yeah, question?
Sorry, Professor. I would like to know if that expression for the energy is actually a Lagrangian for some system that maybe...
If that expression for the free energy is...
For the free energy is a Lagrangian.
You're asking me if it's true?
If we are going to use it to deduce
no, he asked me if that can be seen as a Lagrangian. As a Lagrangian.
Oh, Lagrangian. Yeah. Yeah. Yeah, it's okay. Yeah. And so one of the things you can do, I'm talking here about dissipation of energy. Dissipation. We could also consider the problem of conservation of energy. And Newton's laws, force equals mass times acceleration, and get the the equations and use this energy, potential energy, and then we'd have a different equation. But those are very, very interesting too. Yeah, so you got Lagrangians going on, and you have conserved quantities when you think of those. So we're going to do some collaboration here. We're going to find out what is the minimizer, of this expression. And we're going to do it with collaboration. You can assume that we'll say that J is non-negative, and I'll do the first part and you can do the second part. So I'll make this minimum by making U constant, and then it's 0, okay? And now you have to do your part.
Él dice que hay que minimizar E y que él va a hacer, que él hizo el primer término ya, que es un número constante, ya queda minimizado. Ahora el segundo término, él dice que tiene que ser usted.
You see, I chose first. So. So the question is, which constant? Clearly, U has to be constant if it's going to minimize. So which constant would you like? So this is going to determine the constant. Okay, so you don't know immediately. They are thinking, yes.
I think so.
Yeah, I think you're thinking. So this is the function. We had, oh no, we didn't have that. The pencil, there one. So we had T, K, U minus 1. It's going down. Log will start higher. Sorry, this should be 1 minus U. Oh, I touched the wrong one. This is the paint thing. A return. No?
Yes.
Sorry, another one.
Yes.
Okay. Yeah, where is this is the eraser. Yeah. Okay. So, I hope I'm providing the entertainment too. Yeah, there'll be popcorn coming around soon as well. So we have TK. We'll get it right this time. 1 minus U log 1 minus U plus the other one, which I don't want to write down, with the plus signs. There's that bit, and there was this minus 1/2 J bar U squared. This is the thing we want to minimize. We want to pick a number for U between -1 and 1. And by the way, we can't go outside -1 and 1, and we can't even go 1 because the log is undefined when this expression is 0. This one becomes 0 at 1, the other one becomes 0 at -1. But in between it's fine. All right. All right, we'll do some more collaboration. I'll do this one, and you do this one. So I'm going to draw this, and it looks like, oops. Yeah, sorry, I missed a little bit. I need to do some calibration of my finger. You get the idea. Okay. That's this one. So I've got negative U squared. It's going down at 0, and -1 is here. Negative 1 is here, and +1 is here. Of course, this is defined on the whole line. This one is not, though. So, why is this not working? All right, so what is this? I sort of described what would happen if u went to 1. If u goes to 1, this is x log x, as x goes to 0. And x is stronger than log, and so this goes to 0. Use L'Hopital's rule to show that. So this is 0 at 1, and this is 0 at negative 1, and otherwise, and so this is 0 at 1, and this is 2 log 2, and the other way around, 0. So I'm going to choose a different color. We won't vote on it. I'll just get one. This one. So it's going to be. Oh, I'm still got that, have I? I don't know. At negative 1 and 1, it has the value 2 log 2. 2 log 2. This part. Well, actually, it's multiplied by TK. TK. Temperature times Boltzmann's constant, not to the 2 log 2 power, it's just because my finger isn't right. Okay, get rid of that. All right. You know what it is. But how does this behave in between? Suppose u is equal to 1/2, for instance. You see it is symmetric. It is symmetric. That's nice. I only have to draw half of it. What is it at u equals 1/2? It is 1/2 log of 1/2 plus 1/2 log of 1/2. That's log of 1/2. And what kind of number is log of 1/2? It's a negative number. It's a negative number. These are positive, and this one is negative. Do I have my pen again? It is. So we have this negative number down here, and in fact, if you take the derivative of it, you find that it is a convex function, symmetric, even convex function. Goes like this. Oh, that was there. Okay. We're still trying to minimize this. I'm trying to understand what I have. So I have these two functions. One's going a frowny face and one's a smiley face. And the sum. What is their sum? Let's make the temperature very large. If the temperature is very large, then these go up high, and this actually goes down low, right? Because it's kT multiplied by log of 1/2. So this becomes like this, and this is between -1 and 1. This is T large, T very big. That's a big, big, big. Right, and down here. And this poor quadratic is just overwhelmed by this strong entropy term. There is a unique minimum, and the minimum is 0. That is uniform 0 state. That it's exactly between +1 and -1 at every lattice site, right? It's spread out to become homogeneous, and that's the minimum. But suppose I decrease the temperature, and so this thing, this one is just like this, just a small one. Then you can see that this may dominate that. Right? Well, what does that mean? If you think about it, though, I cheated here. I didn't draw this quite correctly. Even though, this part becomes 0 when we're at 1, and this part becomes 0 when we're at -1, the slope is infinite. There. The slope is infinite. Okay, the slope is infinite, which is important. It means that while this dominates the entropy term, in the interior, at the edges, the slope is negative infinity. The slope of this function is negative infinity here and positive infinity there. Do you see that? So what does a function look like that has negative infinity, positive infinity, but in the middle it looks like a quadratic? Let's go back to this because so here's a picture. Here is t very large, t bigger than tc. Okay, t very large, it is convex. The entropy term dominates, there's a unique minimum. Okay, don't believe this scale, I don't know how to make scales. But, and then, as the temperature decreases, that quadratic term starts to dominate, and at some critical temperature, it flattens out in the middle, but still has infinite derivatives at the ends. And then after that, do I have a picture of that? Oh, don't. All right, let's go to the next page or something. I'm drawing. I want the hand. All right, I'll draw a little one here. So we have this. It's infinite. It's like this. Oh, like that. It has two wells, two minima. And this is the origin of phase transition occurring at a critical temperature. You lower the temperature and you lower the temperature, and then suddenly two minima come out of the one minimum. They are ordered. So I'll have an island of gold here and an island of silver here. And they tend to congregate. The islands get bigger and bigger. And we call this coarsening. As I talked about granite, if you cool slowly, they tend to get bigger and bigger lumps. Of course, to get a big lump here, something had to be lost from here, right? So big lump of gold means less gold over here. There's migration, and if you have a little lump of gold and a bigger lump of gold here, the bigger one wins. This sort of dissolves and the bigger one wins. Survival of the fattest, which is what I've done to survive. So, so that is something. And now I'm going to fix the temperature at a subcritical level and write down the free energy like this. Temperature is fixed. Boltzmann's constant is constant. Okay, so that's constant. And so the function that I had with the logs and everything in it, I'm calling W because that's what it looks like. Right? Looks like W, subcritical temperature. And because I didn't know where those two minima were, I could calculate it, but some number. I'll do a scaling so that the minima will be at plus or minus 1. Instead of plus or minus alpha, I'm going to change the name of the variable or something. I'll have that occur at plus or minus 1. It's not the entropy for plus or minus 1. It's just now we're just doing mathematics. From now on, it's just mathematics. Forget the physics. We have a model. Yeah, so this is the scale to take alpha equals 1. Yes, I should mention this. When you have an external force acting, you could have an electric field or another magnet that's helping these things choose a different value than they would have chosen just based on their neighbors. So what that does is change the depths of the wells if you have an external force. It becomes a linear term in that expression with the logs and the u squared. So it changes the depths of the wells. But I'll still call them plus or minus 1. It's just that they may look like this. Okay, so that energy state, this free energy, is looking like this. And this is on the energy of a state on a lattice. We have a spin field on a lattice. Or it may be concentration of gold and silver. Let's say U represents just the mass fraction of gold at the point, lattice point R. I mean, you know, on average. But when we're dealing with materials, we also like to think of continua. So instead of a sum, a sigma for a sum, we use an S for sum. And it's a double integral over Rn. We have an n-dimensional lattice, so that's Rn cross Rn. That's the double integral. There's the J as before. And instead of U of R minus U of S, it's U of X minus U of Y squared. Integrate with respect to Y. And there's the sum of the W of U again. So that's a continuized version. Seems reasonable, right? You're supposed to say yes, it seems reasonable.
For physical meaning, n should be 3, I suppose. Or
The dimension?
yes.
I don't know. What dimension do you live in?
Yeah. Yes, but it's for the...
Yeah, it can be anything. I mean, we could be doing string theory here or something where
Yes.
you're 10-dimensional or whatever.
O sea, en ese número de dimensión donde están metidos materiales.
But as I said, we're doing mathematics now. We're not doing physics. So n can be anything. We're doing mathematics. So it's going to be general. It's going to have no application, but we'll enjoy it, I hope. What happened here? Yeah, so that's that. So, again, this is what I mean by non-local interaction. This is interaction as x and y are arbitrarily far away in Rn. There's going to be a contribution there. At least if the J has infinite support. If J is non-zero, far out. So now, how did that happen? I don't know. Now, this is okay. So the evolution. So I started out, well, somewhere back there I said, how is it going to evolve? I first said, why is it going to evolve? Why is it going to change? Now we know the why. So we know something about forces, potential energy and the tendency to decrease. And now I say, well, okay, so how will it decrease the energy? And something like the second law of thermodynamics, just, you know, it really says energy decreases. But we feel like it should decrease in the most efficient way. You know, efficient decrease. I want a new page. So I got to get a new page, yeah. Somewhere. There. No? Selection. Rectangle. Oh no, that's select. Okay, never mind. Hage. Blank page, yeah. Nice one. Right there. Oh. Okay, yeah. All right, good. Where was I? What was I talking about?
The rate of the decrease.
Yeah, how things will decay. So, is there anybody here who has not taken vector calculus? You have not?
I'm about to.
You're about to? Okay, so this will help you. This will prepare you for vector calculus. It's actually very easy. This part is easy. Suppose I have a function z equals f of xy. Yeah, sorry, let's go raise it's a bit slow, this, isn't it? F of xy. So a function of two variables, and it looks like this. I'm getting good at this, aren't I? No. Okay, so this is the x, y, no, okay, I'm not good at it. XY plane. How does it do that? Okay, it's the XY plane. You can't read that, I know, but come on. Doesn't want to erase that part. Okay, so we have the XY plane and we have this function, and the function, I'll have it this color. What color? Oh, this one. You're not supposed to laugh at professors, you know? It's very rude. Okay, so fill that in again. Okay, so this is the function f. F, z equals f, this axis. And here we have the xy plane. And we have this, this is supposed to be a function, okay? This is distortion of vision or something. And I am at this point here, x 0, y 0, comma. Okay, I'm at this point. And here is the energy, or here is f at that point. And I want to move this point along a path in the xy plane so that the energy, the f, decreases most rapidly. Decreases most rapidly. How many people here have walked on a mountain? Well, you live on a mountain. Okay. You know about gradients of mountains, like you know about steepest way down. And if you go like this, you see these roads and paths. People don't like to go down the steepest way often. But if you want to get down fastest, okay, I'll go the steepest way. Right, steepest descent. The direction of steepest ascent is called the gradient direction. And it comes out of just the partial derivatives, grad f, that's an r there, at AB equals f sub x. How does that work? Okay. I need a better finger. F sub x at AB. Okay, I'm not very good at this. F sub y at AB. Okay, it is a vector, it is a direction. So we look at this, and we look at the shadow of this on the floor, and it says at this point, take off in that direction. You know what I mean? At this point, there's a direction to go which instantaneously takes you in the direction. It is the negative of that. This gradient is the steepest ascent. We go backwards. We go down there. That is the fastest way to go down. That's the most efficient way to go down. All right, so that's nice to know. And as I go down, I'll keep changing the direction because this function will change. I'm moving from point to point, I'm moving, and so this function could change, and I may go in a wiggly direction here so that I go down most rapidly here. All right, is that okay? All right, so so this would be like a dynamical system, an x dot y dot y dot equals f sub x at xy and equals f sub y at xy. And this would take you uphill fastest, and if I put a minus sign there, that will take you downhill in the fastest way. It is an autonomous dynamical system. It's just a dynamical system in the plane, but it's determined by this potential energy, this free energy in our case. All right, so now that's what I'm going to do. Only the difference is, which one do I have? Yeah. Instead of this being two-dimensional, each point here has a name like U. What is U? It is a distribution of spin or distribution of gold. It's a function defined on all of my domain. So this is a function. Every point here is a function. All of the functions are in here that I'm dealing with. This is an infinite dimensional space. This is infinite dimensional, but this is still a one-dimensional axis that measures the energy of each state, each function. Okay? Sometimes, we call these functions fields. I don't know, it sounds fancier, but the functions. So, we now have infinite dimensional space of functions of x, say, functions, distributions, functions of lattice position, and here we have the energy, the free energy, and it has some shape. It's a graph over infinite dimensional space, and at each point we're going to go down most rapidly, like this equation says. Right? That's going to be the second law of thermodynamics. So for the people who are in graduate mathematics, and that's why we have grad E here, for graduate math, no, that's gradient. You may know that if you have an infinite dimensional space, a Banach space, and you have a nonlinear functional on that Banach space, that is a mapping from the Banach space to the real numbers, and you take the derivative of that, which you can do, what you get is not a member of the Banach space, you get a linear functional on the Banach space. Okay? Now when you're in Rn, the functionals are the same as the vectors, and they operate by dot product. If you're in a Banach space, in general, there is no member of the space which represents the functional. But if you're in a Hilbert space is where you have an inner product, like a dot product, but an inner product between functions, and I might as well tell you that. Suppose you're in Rn. What is the dot product between x, which is x1, x2, x3, and xn, with y, y1, comma y2, y3, yn? How you do the dot product? You multiply the first components together, you multiply the second components together, you add them, you multiply the next pair, and you add them all up, right? With functions, you do the same in the Hilbert space called L2. The dot product there is, I'll take my function at position x is like the index, I'll take my function with index y, so u of x, u of y, I'll multiply them together for each, sorry, erase your memory. Have you seen Men in Black? So you have u, I'm taking the inner product between function u and function v. Okay, I'm back on the track now. So you have u of x times v of x with the same index, x, and then you add them all up over all the x's. But adding them up means integrate, right? It's the same thing. So that's the inner product in function space. The one that's called L2 means the square of the function is integrable in the Lebesgue sense. Very fancy words, but you know what integration is? It means if you square the function, you can integrate it, basically. So 1 over the square root of t on 0, 1, 1 over the square root of t, if I square it, I'll have 1 over t, but I can't integrate that, it's infinite. So that is not in L2 of 0, 1. But if I had 1 over the 4th root of t, 1 over the 4th root of t, am I able to do this one? Let's see. If I do 1 over the 4th root of t, I square that, I get 1 over the square root of t, I integrate that and I get t to the 1/2 with some number in front. And t to the 1/2 can be evaluated at 0 and 1. So some functions that are infinite in a place are in L2 and some functions are not. So it's a little bit of a technical thing. But anyway, we need that for the inner product to work because we've got u of x times v of x. And if v was the same as u, I'd have u of x squared. And I want to be able to integrate it. So in that space, I'm going to look at this. And the gradient is the representative of that linear functional by a member of the space. So don't worry about it. But the representation through this inner product, this dot product. Okay. Now, okay, so fine, that's all abstract nonsense that I could hardly understand. How do you calculate the gradient of a functional? Well, how do you take a derivative? Well, you know, when I was doing that picture down there, I was actually interested in the derivative in a certain direction. So you look at directional derivatives, actually. So here's what you do. I'll take E, U plus H, this is a number, times V, V is a direction. I'll take D by the H of that and set H equal to 0. What that does, I know this is a mess now, but here's another point. If I want, here I am at U, and I'll take the derivative in direction V. Oh, that worked. V. So I'll look above that line segment, and I'll see this thing. This has shadow that, right? If I have a light above here, and that curve, that's just a curve, you know, above this straight line, I'm going to take the derivative at U in the direction V. And what that means is, oh, you look at that from the side, and it's just a curve in two-dimensional, you know, X and Y. Right? One direction V and the vertical axis. You know, this is X, Y. So what we're doing when we take the derivative in the direction V is finding the slope of the tangent to that curve in one, you know, in this direction. So everybody knows about that, right? You know how to do that. You just express your straight line as U plus HV, and you take the derivative with respect to H and make H equal 0. That's how you do it. So now, if I had this, how would you take the directional derivative of E of U in the direction V? Well, I just had it. I'd have U plus HV, so U plus HV, U plus HV of X minus U plus HV of Y, and here I have W of U plus hv of x, right? And then I take the derivative with respect to h, and we saw where the h's were. And if I can take my derivative through the integral sign, which every engineer does, which sometimes you cannot do, but we're okay. If you take the derivative through the integral sign, then this is just, you know, first semester calculus, the first calculus that you saw. You just take the derivative. You got a square here, the 2 comes down, and you get this, and a v comes out, you know, because you have to use the chain rule. Here you get w prime, u times v, and then you express that as an inner product of something with v. Okay, so after you do this, you say, oh, I can't draw on this, can I? Oh, can I? Maybe I can. What does that do? No. You'd say this is equal to, I'd write down those integrals, and I'd do the calculation, and I'd have the integral of something times v. I'd separate it all out, I'd do my arithmetic, so it was something in u times v. And this is what you would get. This is the negative of the gradient. This is the something of u times that would be multiplying the v. This is the gradient, the negative of the gradient. Where this is convolution, this is just a number k. K is the integral of j. That's like, you know, that j bar. And there's w prime of u. Just regular calculus. I nearly stole your drink there. I saw a bottle there now. So in the discrete case, the convolution is that. It's convolution. The NAC is for non-local, because this has the non-local interaction in it. Alan Kahn. John Allen and John Kahn, a material scientist. Well, John Allen is dead. John Kahn is retired and is in Washington State, I think, now. So he's a guy I know, but he's a very famous material scientist. The Alan Kahn equation is everywhere. Well, this is a non-local Alan Kahn equation. And this is without a compromise. You know, this is doing it right with interaction everywhere. But I wanted to point this out, that this interaction term in the energy, you could say, you know, that equation that I had was fairly hard. Oh, I'm so old. Was hard to work with. So actually what Van der Waals did a long time ago, he said, u of x minus u of y. I know the mean value theorem, so that's like the derivative of u times x minus y. And this is at x, so not at some point c in between x and y, I'm putting x there. Why is this any good? Because the j, if the j decays very rapidly, then x and y are close together, and the u is differentiable. So u of x, u of y, they're some more or less the same thing, u of c, right, gradient of u of c. So you could do that, and then this term becomes this. One of the integrations you can do, because you have x minus y here and x here, I could do yes, I would do the y integration, and I have the j of y. I would anyway. The epsilon squared is the second moment of j in any one direction. This is a yi. And this you get a gradient squared because this thing was squared. I mean, you can see that, what did I do? I know. Okay. Yeah, sorry. I get that term, and then if you do the L2 gradient flow of that, you get the Allen-Kahn equation. And this equation comes up in so many areas, genetics and material science, in neuroscience, in anything that has diffusion and two stable states. This is what van der Waals actually did in 1893, because he could understand derivatives, but he couldn't understand how to deal with this long-range interaction. And he justified it by saying, well, x and y are close when this j is decaying reasonably well. And after that time, everybody considered the functional, which is called the Ginzburg-Landau functional, with a gradient u squared. All the physicists and people, and they're wrong. So since the end of the 1800s, they had the wrong thing in there. At least if you have interaction occurring at all ranges. Of course, you might say, well, this really is close, but you cannot say this approximation is uniformly good over all choices of function. This approximation is a good approximation for one function, provided the support of j is sufficiently small. But given another function, like sine 1000x or something, then you need to know about all this behavior. So this is a very bad approximation, in fact. For each function it could be a good approximation, but uniformly it is a bad approximation. But nevertheless, everybody has been dealing with the gradient squared functional. And this is the Allen-Kahn equation, and the natural boundary condition is this no flux boundary condition out of the... what? I've been going for an hour and 27 minutes. I'm really having a good time. Sorry, you can leave if you like. I'll continue it. So now we have an equation. Does anybody want to go and get a drink, go to the bathroom, escape? I'll finish in, I don't know, 20 minutes.
They are used to 2 hours lectures.
It is a 2-hour lecture normally?
Yes.
Okay, but are people going like this? Yeah, I have a bottle to drink. Okay, so we started out by saying, this is what materials look like, and why do they change? And we've figured out, they change because of this. And then we said, how do they change? And we got an equation, which is this equation. The derivative of the state, the function, with respect to time, because we've evolved with time, according to this spatial convolution, minus this term, minus that term. And by the way, this w function was like this, right? It was like that. The derivative of a function like this, it starts out with negative derivative, so it's negative. In fact, the w looked like a degree 4 polynomial. And then physicists sometimes talk about the phi 4 potential. And that's because it looks like a quartic, and they replace it by the quartic, in fact. So when you take the derivative of a quartic, you get a cubic. And the cubic will look like this. It'll have a negative, so the derivative function is negative for a while, then it becomes positive, then it goes down, and then it becomes negative and positive again. It's a cubic-like thing with zeros at plus and minus 1, and at the intermediate critical point, which is the hump. The plus and minus 1 are stable, and on the hump that is unstable, as you might imagine. This is bistable dynamics, and this part, that's the sum of j, so that's part of the non-local term, the interaction term. Okay, so this so we have that equation, and now so we know we've guessed at why it changes, we've guessed at how it changes mathematically, but really, how should interfaces move? So we'll suppose that the coarsening has occurred and there's a big blob of gold over here in a sea of silver, and I want to know how the interface of gold will change. Or if I have a big group of positive spins in a sea of negative spins, how will the interface move? Maybe there's an external field, so one of the wells is deeper than the other. So it all wants to go to the deeper well. So we have to look at that equation. And typically, when we look microscopically, we'll say, yes, this interface, microscopically, looks like a plane separating one phase from the other phase. And it will move one way or the other, perhaps, or it may stay there. But I will guess that the state will change with time according to this. So x dot a, x is the position vector, dot a is a direction vector, plus ct, where c is the speed and t is the time. You notice that if I move in the direction A, then you'll have the same profile u, just evolving with time. It's like a really perfect surfing wave that just goes like this across. The wave, the shape stays the same as we move across. So I want to know how that would move. So let's, instead of writing w prime, we'll write f, and we'll suppose it is a cubic, so we can think about it a little bit. And I will do that in the non-local equation, and I'll do it with the Allen-Kahn equation too. So we've created from our n plus one-dimensional set of variables, independent variables, we now have one independent variable. Just this expression. It's it's a scalar variable, z. I can call that z. And when I take the derivative with respect to t, I'll use the chain rule. I'll get u prime times c, right? And when I take the derivative with respect to the spatial variable, out will come an a. Where are we? Yeah, out will come an a when I take the derivative with respect to the spatial variable. Only I didn't do that. Oh, but a is a unit vector. Yes, a is a unit vector because it's just the direction. So here you see I had u sub t equals some stuff. Well, I take the u sub t to the other side and then it equals 0. There's c u prime. That's the u sub t became that. And this is the spatial derivative. It was Laplacian, but in one dimension it's just u double prime. Okay, second derivative. And we'll say that the wave will go like this. So it'll have a transition from this state, say -1 spin, to this state plus 1. It's not the spin, it's what I relabeled alpha, plus or minus alpha. Okay, so we'll have a transition so that at plus infinity we're at one stable state, at minus infinity we're at the other stable state. And because we can move this wave anywhere we like, we have to decide on the coordinate system. I'll say where it becomes 0 is at 0. So now we have this profile, and I want to find the profile u, and I want to find the unknown speed c. I've chosen the direction, but I don't know how fast it's going to move, or if it will move, or which, forward or backward. And I want to know what the shape of the wave is. So, so if you've done beginning ordinary differential equations class, you wake her up. I have a lulling voice. If you've done a differential equations class, I don't remember how to get a new page, but second order nonlinear differential equations you can study using phase plane analysis. Right, you have a u and a u prime axes, and you show curves of trajectories, how this function behaves. This is, with this cubic, this is easily understood. There is a unique transition state, and it will go in the direction so that it becomes, everything is going to the lowest energy state. If the energy levels are the same, why move? Those minima, why move? So it doesn't move. But if they're off, and one is slightly below the other, they will move. And the speed c, you can actually calculate the speed c by multiplying this by u prime and integrating between minus infinity and infinity. This will give me u prime squared over 2 at plus or minus infinity, which is 0 because it's flat at plus or minus infinity. That goes away. And the integral of f of u prime gives you capital W, right? Because little f was the derivative of w. So you get w at plus or minus 1, which is w at 1 minus w at -1, and it is the difference of the depths of the two wells. C times the integral of u prime squared is the difference of the depths of the two wells. So if I divide by u prime squared, my students hate me doing this, not writing on the blackboard and describing the mathematics. It must be even really horrible in another language. I'm doing it, I'm sorry. Yeah, I get carried away. I wave my hands and look at this. Yeah. Anyway, it's almost like the speed is proportional to the difference of the wells, difference of the heights of the two wells. This has 4 wells, actually. Yeah, and if I tilt it, one is lowest, so it would go there. So that's how it works with the Allen-Kahn equation. You do get a unique profile and a unique speed and you can calculate that speed more or less for the traveling wave. For the non-local Allen-Kahn equation, you do the same thing. You integrate little j perpendicular to the direction of travel, so n-1 direct. And let's say this is equal to 1. And then instead of little j, I'll have big J. Big J depends only on one variable now, right? The direction of travel variable. So we have big J convolved with u minus this, because J is equal to 1, integral of J is 1, so instead of a K there, it's just 1, minus cu prime and so on. Same boundary conditions at plus or minus infinity and 0 at 0. And I look at that, and this has a derivative on it. But this is convolution. The whole infinite dimensional nature of U is involved in that. So when you see this, you say, this is easier. This is a one-dimensional differential equation, but it's not. It's an infinite dimensional differential equation. I don't know how to do phase plane analysis in more than 3 dimensions, never mind, 2 I can do, 3 I can sometimes do, but not beyond. So phase plane analysis is right out, forget that. And so, and another point, what if the speed turns out to be 0? Then it's not even a differential equation, right? If the speed is 0, there's no derivative. So, to cut a long story short, to be merciful, I will just describe this fairly quickly. Here is a parameter lambda, which is going to go from 0 to 1. And if you look, when lambda is equal to 0, I get u double prime minus cu prime minus f of u. That's the one I understand by phase plane analysis. When lambda is equal to 1, this is gone, and it's the one that I want to understand. So this, as lambda moves from 0 to 1, this is going to be a deformation from an equation I understand completely to one that I really want to understand. We call this a homotopy from one equation to another. Why we invent these words, I don't know, but anyway. And so we're going to perturb. We're going to start with lambda equals 0, and we're very happy, and then we're going to perturb a little bit. Lambda is 0.00001, and see if we can do something with that. We want to find a solution. We would like to know if there's a unique solution when we perturb from lambda equals 0. And there's an important theorem in mathematics called the implicit function theorem that says you have unique continuation with respect to perturbation if the derivative of the thing that this thing in the u direction, c direction, is non-degenerate. I'll show you the implicit function theorem. Suppose I have a function over this floor, and at this point it's equal to 0. The function goes through that point. I would like to know if I change my function a little bit whether it still becomes 0. Well, here's how you do it. This is the implicit function theorem in a picture. Let's suppose this axis is the lambda axis. Okay, that's the perturbation axis. And this direction is the u axis. And here is my function becoming 0. Actually, this is the tangent of my function. This shows the slope of my function. If my function has a non-zero slope when it goes through that point, then the whole surface with the lambda and the u has to go through the floor. Right? Obvious. That's the implicit function theorem. Okay. So you can do that in infinite dimensional space. And you can get solutions. And you find, the analysis is kind of interesting. You find that even when the wells are different heights, the speed may be 0, which doesn't make sense quite. You'd think, that's not right, it should move, it should migrate. But the operator convolution is not the same as the operator which was the Laplacian, which is diffusion. One is a bounded operator and one is an unbounded operator. The non-local one is a bounded sort of diffusion, and it sometimes does not overcome the nonlinearity. There's a balance. Whereas when you have the Laplacian, it always comes. You know, the Laplacian's wrong because of what I said. It's wrong for other reasons. Have you heard people say, when you strike a match, you feel the heat before you see the light? Have you heard that? Because diffusion travels to infinite distance immediately, whereas light obeys an equation that gives you finite speed of propagation. Well, similar thing here. This gives you only a finite speed, and actually it can stop you moving. The interaction can stop you moving. You may believe that on a lattice, right? On a lattice, it's a lot to jump. You know, if I've got to exchange positions with that gold, I'm silver. Okay, come over here, I'll go over there. You know, there's a tendency not to do that unless the energy really demands that I do that. So you can have what's called pinning of waves. And because you can have pinning of waves, you can put many of these waves together and get stationary solutions which undulate up and down and arbitrarily distance between them. And if we're in several space dimensions, you get tremendous patterns that are possible by this non-local diffusion equation. And the function may not be smooth, it may actually be discontinuous, the state. And here's waves on a lattice, there it goes. And here's a bunch of analysis about how you do it on a lattice. There it goes. And oh, it's still going. Oh, patterns now. Okay, patterns. There they go. Okay. Oh no, it's still going. How are you doing for time? And okay. All right. So, muchas gracias. I appreciate your patience. You're very, very good. I would have had a rebellion.
Nicolas, did you cover in the first step of the exposition with Jamie using the...
This exposition, I was going in steps, sort of. I mean, I was saying, how do you model this, and then what happens, and then try and analyze the equations. And I didn't give you much analysis of how the equations are analyzed. If I'm looking for a traveling wave, I do this homotopy method, and my analysis leads me to conclude that sometimes you may have stationary solutions even when the wells are an equal depth. And precisely the condition under which that happens. It's, I just speak too much. You know, I had a lot more there. But I'll leave the slides. If anybody wants to have more of this, they can look at the files of this. Not quite complete. I didn't include the necessary and sufficient condition for speed zero. It's a necessary and sufficient condition. But I'll try and find that. But maybe I didn't answer your question. I just talked.
My question is, in one part you talk about conservation law.
Sort of, yeah. So if I'm looking at silver and gold, we're not very good at changing one to the other. So there's conservation of species. Mm-hmm. But when we have spin up and spin down, there's no conservation, mm-hmm. and you have dissipation. So actually, we think we're on an infinite lattice or an infinite place, and well, you might have conservation of gold. It's going off to infinity, and so locally, you don't see the conservation. But if you really want to see if you really want conservation, then you can modify the equation to include a constraint of conservation, or you can increase the equation to what's called the Cahn-Hilliard or the non-local Cahn-Hilliard equation, which automatically gives you conservation, which they developed for a binary alloy where you have conservation of species. The Allen-Cahn equation was developed for non-conservation systems like, you know, water to ice or spin up, spin down kinds of systems. So yeah, I brushed over that. So you caught that. Yeah, but we can consider both types. Yeah, thanks.
¿Alguna otra pregunta?
Yeah, he says, when can I leave? I was worried about this guy. Let's see your t-shirt. Your t-shirt has something about a revolution.
No.
No?
Quiero ver su camiseta que dice.
Yeah, repression. Because of repression, that's revolution. I'm repressing the guy. He's a troublemaker there. Yeah. Hi.
You said we can see the files.
Yeah.
How can we?
Yeah, I don't know.
Send you
I'll give it.
With the certificate.
Yeah.
Los que quieren el certificado lo solicitan y los depositantes lo solicitan a vuelta de correo. ¿Alguna otra pregunta? ¿No? Bueno, entonces mañana es a las 10 de la mañana, acá mismo.
But you may want to ask the question, how long will it be tomorrow? Or maybe you want some input on that. So you can tell him, I will come if you promise it's only 45 minutes, or if it's only an hour. So you can tell him that. You don't need to tell me. I'll go on believing that you love this. Okay, so anyway, thank you very much.
Okay.
And I'll stick around if anybody wants to talk.
Mañana es sobre morfogénesis, morfogenética, la cuestión de la morfogenética es un tema bastante interesante, como sobre los huesos, la forma de las células, bien. Los que quieren pueden hablar ahorita con el profesor y nos vamos a tomar una foto aquí en las escaleras de la morfogénesis los que quieran. Bueno, gracias.
Oh, thanks. So you have the file there now, right? You have the file.
Send to me the file.
Oh, that's better, right? And I want to get my stick out of there. I know there's something down here which will get rid of.